In this video, we're going to go over how to solve linear systems of differential equations using Laplace transforms. So we've spent some time going over how to solve the homogeneous system with constant coefficients. You use the matrix exponential. But sometimes you have non-homogeneous system. So a non-homogeneous system in the 2 by 2 case is you have x1 prime, x2 prime equals the matrix, say A, B, C, D, times x1, x2, plus some function of, say, t, so g1 and g2. So g1 and g2 are functions of t, just like x1 and x2. Suppose that you have also some initial values, x1 of 0 equals k1, x2 of 0 equals k2. So in this video, we're going to go over how to solve this general system. And the idea is to use Laplace transforms. So let's just set up some notation. Let's call capital X1 the Laplace transform of little x1. And usually I'll use S for the independent variable of capital X1. Similarly, capital X2 is going to be the Laplace transform of little x2. And the G1 and G2 that make up the non-homogeneous part, those will also have Laplace transforms. So let's call them capital G1. So G1 is a function of S, and capital G2 is the Laplace transform of little g2. Usually I just neglect the parentheses S because it just clutters up the equations. So here is the idea. So first let's write out the system of equations without matrices. So if you write that out, you get little x1 prime equals a x1 plus b x2 plus g1. x2 prime equals cx1 plus dx2 plus g2. That's what we're solving for x1 and x2. So now you take the Laplace transform of both sides. And in this video, I'm assuming that you're familiar with the Laplace transform. And that you learned the formula for the Laplace transform of the derivative of a function. The Laplace transform of x1 prime turns out to be s times the Laplace transform of x1, so that's capital X1, minus the initial value, x1 of 0. So that's what I call k1. So I get little s times capital X1 minus capital K1. So reminder that capital X1 is a function of s. Capital K1 is just a constant, right? So capital K1 is like 5. So this is equal to the Laplace transform on the right-hand side. And there is this linearity property that the Laplace transform of a linear combination of the functions, okay, the linear combination of the outputs, is the corresponding linear combination of the Laplace transforms. So I just get A times the Laplace transform of little x1, that's capital X1, plus B times capital X2, plus the Laplace transform of little g1, that's capital G1. Similarly, I have S capital X2 minus capital K2 equals C capital X1 plus D capital X2 plus capital G2. That's the equation I get by taking the Laplace transform of the second equation. So now I have these equations. Now let's do some algebra. Let's get the x1 and x2 on the left side and move the k1 and k2 to the right. So if you do that, that's going to give you, it's going to imply that I get this system of equations, s minus a times x1 minus b x2 equals g1 plus k1. And negative c x1 plus s minus d x2 equals g2 plus k2. So all I'm doing is I'm just moving. How did I get this? I moved the ax1 to the left and the k1 to the right and subtracted the bx2. And then for the second equation, I just did the same thing. Moved the cx1 and the dx2 to the left and then moved the k2 to the right. And this is what you get. Now I can rewrite this as a matrix vector equation. So this is going to give me this matrix S minus A, negative B, negative C, S minus D times capital X1, capital X2 equals capital G1 plus capital K1 capital G2 plus capital K2. Well, what is this matrix here? This matrix, so we started off with this matrix A, B, C, D, so let's call this capital A. Now if you take minus capital A, that's just minus A, minus B, minus C, minus D, and then this matrix that I have is pretty much that except with the S's added on the diagonal. So this matrix is SI, I being the 2 by 2 identity matrix, minus A. This matrix times capital X. So capital X is just this, what I call this vector, and then equals, and I'm going to write this as capital G plus capital K. So capital G and capital K have the obvious meanings. Capital G is just, I don't know, do I need to write this down? I think it's pretty obvious. The capital G, I refer to this, okay, and then capital K means this. So that's my notation. So I get capital G plus capital K. And now it's easy. I can solve for capital X, right? Because I just multiply by the inverse of this matrix. So I get little si minus A inverse times the matrix G plus K. That gives me my capital X. And finally, I just take the inverse Laplace transform of the components. So if I take the inverse Laplace transform of capital X, I get little x, right? I get the vector of x1 and x2. So this is the inverse Laplace transform. So take inverse Laplace transform of both sides. I get little x of t equals the Laplace inverse Laplace transform of Si minus A inverse times G plus K. So that's the answer. So let's just review. So you have this 2 by 2 system, non-homogeneous, and you basically just do the algebra. So you write this out, the systems, and then you take the Laplace transform of both sides, and then you get this formula. You multiply by the inverse of Si minus A, and then you take the inverse Laplace transform, and that gets you back little x1 and little x2. So now let's look at a simple example. Solve x prime equals this matrix. First row is 0, negative 1. The second row is 1, 0. X plus 0t. Now this has a bunch of zeros in it that make doing this a lot less tedious. In general, that's going to be really annoying to do. So here's my non-homogeneous system, and then when you plug in 0, you get capital X1, capital X2. So just arbitrary initial conditions. The question is to solve this. Well, I have the formula. I have the formula for capital X. I need Si minus A inverse. Well, this is my matrix A, so my Si minus A is going to be S on the diagonal, so I have S minus 0, and then minus 1, 1, S. Right? So that's my Si minus A. So now I need to find Si minus A inverse. And I just use the formula for the inverse of a 2 by 2 matrix. So the determinant is S squared minus -1. That's S squared plus 1. So 1 over S squared plus 1. And then I flip A and D, so I get S and S. Then I keep B and C the same, but multiply by -1. So I get this. So this is my inverse of Si minus A. Okay, now I also need the Laplace transform of these functions. So this is my little g. I need the capital G, the Laplace transform. Well, the Laplace transform of 0 is just 0. The Laplace transform of t is, okay, what is it? It helps to have a table of Laplace transforms. It turns out to be oh, wait, hold on. Let's see. 1 over S squared. Okay, 1 over S squared. So now I need my G plus K. So my G plus K vector is 0 plus K1, and then 1 over S squared plus K2. Okay? So that implies that my capital X is 1 over S squared plus 1 times this matrix times this vector. And now you do the matrix multiplication. So you get capital X1 of S, okay, equals K1 times S minus 1 over S squared minus K2 all over S squared plus 1. That's the first one, and then the second one is K1 plus 1 over S plus K2S over S squared plus 1. So those are the Laplace transforms of little x1 and little x2. Right? These are my capital X1s, capital X2. That's the Laplace of little x1 and little x2. So now I need to find the inverse Laplace transform. How do I do that? So I have to rewrite these guys. So let's look at capital X1. So I'm going to split the fraction up. So I'm going to get K1. I'm going to move the constants outside. And so when I do that, I'm going to get capital K1 times S over S squared plus 1. And then minus 1 over S squared times S squared plus 1. Then minus K2 times 1 over S squared plus 1. Now I need, so here I can use the table of inverse Laplace transforms for this first one and for the third one. For the middle one, I have to use a partial fraction decomposition. So, okay, I'm just going to rewrite it. So I get minus, so I'm going to split this up into S squared and then S squared plus 1. Now for something simple, where the numerator is 1, often you can usually kind of just by trial and error guess what the numerators are going to be. And I think that if I pick 1 and 1, things will work out. Because you're going to get S squared plus 1, and then an S squared. So those are going to cancel, and then you're going to get a 1 on the top, right? So this is correct, and then minus K2 times 1 over S squared plus 1. So now I'm ready to find the inverse Laplace transform. So I have my table of Laplace transforms ready, and then I'm going to see that it's capital K1 times cosine t minus t plus sine t minus capital K2 sine t. So that's little x1 of t. Now I need little x2 of t. Well, my capital X2, I just do the same thing. I'm just going to split up the fraction and pull out the constants. And when I do that, I get this. And now I have to do another partial fraction decomposition in the middle. It splits up into 1 over S minus S over S squared plus 1. Another instance where you can instead of actually writing out the whole partial fraction decomposition and multiplying by the denominator and doing all of that, for something this simple, it's usually easier to kind of just guess and check which one is going to work. So like for this one, I know that I need to get a 1 on the top. So if I have my s and s squared plus 1 on the bottom, so I need an s above the s squared plus 1, so that when I cross multiply, I get an s squared, and then that has to cancel with the s squared in the s squared plus 1, and so that is going to work. So it takes some trial and error, but that's a little faster than actually trying to write out the entire partial fraction decomposition and solve for the coefficients. So anyway, you're going to get this plus k2 times s over s squared plus 1. And now, again, I find my inverse Laplace transforms using my table. Capital K1 times sine t plus 1 minus cosine t plus capital K2 times cosine t. And that's little x2. So that's the answer. So just a review of the method. We basically found the formula just by using the Laplace transform theory. And once you find the formula, it's pretty simple. It's just kind of annoying because you have to take the Laplace transform of the little g's, right? Your g1 and g2 in the non-homogeneous part. And then you have to do a matrix inverse calculation. Where do you have to? Here, right? There's a matrix inverse, so that's annoying. And then you also have to find the inverse Laplace transform, which is also annoying. So it's not necessarily the fastest, but there isn't really a fast method for solving non-homogeneous systems. So this is actually possibly the fastest it can be. In the next video, I'm going to go over a general formula for solving this non-homogeneous system. That's going to involve the matrix exponential. And I'm going to use that formula and solve this example again.